Greetings everyone, I'm Purna Chandrasekhar. I'm going to talk about applications of diode as a part of my ELL101 project. So the topics that we're going to cover here are diodes as voltage multipliers, diodes being used in solar panels. So before we proceed further, we would recap briefly about diodes. So diodes are two terminal devices that conducts current in primarily one direction. Ideally, the diode has a very low resistance on one side and a very high resistance on the other side. In ideal case, this low resistance takes the value 0 and this high resistance has the value infinite. There are two conditions pertaining to a diode. The first is a forward biasing condition where the positive voltage is applied to the P junction of the diode and the negative to the N junction of the diode. And in this case, the diode acts as a closed switched component. In the reverse bias condition, the positive is applied to the N junction of the diode and the negative voltage to the P junction of the diode. And then in this case, the diode ideally acts as an open switch component. With that said, let's talk about diodes being used as voltage multiplier. The first kind of voltage multiplier we're going to talk about is a full wave multiplier as given in the circuit. As we can see, the input voltage is a full sinusoidal wave, and then we have two diodes which are placed opposite to each other in the sense that at one given instant, only one diode will be forward biased and the other would be a reverse biased. We have two capacitors connected in series, and ideally we should expect the output voltage to be twice the magnitude of the input voltage. So let's analyze the working of a full wave multiplier. When sinusoidal voltage is positive, this D1 is forward bias, and thus capacitor C1 gets charged through diode D1 and assumes the maximum voltage V in. When sinusoidal voltage is negative, D2 is forward biased, and thus capacitor C2 gets charged through D2 and assumes the voltage V in. Thus, the output voltage is taken across two capacitors which are connected in series. So V in is the maximum of C1 and V in is the maximum voltage of C2. So both of them added together, we get the output voltage as twice the input voltage. Another type of voltage multiplier we're going to see is a DC voltage doubler, where we are essentially having a half signal given as the input, and we're expecting the output voltage to be twice the input voltage. So during the negative half cycle of the input voltage, D1 is forward biased, whereas D1 is forward biased, and thus capacitor C1 is getting charged through D1 and assumes the voltage V in. At the same time, D2 is also conducting through D1, and then it would also charge the capacitor C2. During the positive half cycle of the circuit, diode D1 is reverse bias, so the capacitor C1 is blocked from discharging, while diode D2 is forward biased and it's charged. The capacitor C2 is further charged. Now, in the first case, C2 is already charged to its maximum limit and it has a value V in. And even in the second case, the capacitor C2 is getting charged. Thus, C2 has charges to twice the peak voltage value of the input signal, and thus the output signal is given by the voltage across C2, which is twice the value of the input voltage. In this case, we can use the concept of voltage doubler in circuits and construct circuits which triple or quadruple the input voltage. This is a voltage tripler circuit where the output voltage is thrice the input voltage, and this is the quadrupler circuit where the output voltage is 4 times the input voltage, and both of these circuits are constructed in a similar way as to how the voltage doubler circuit was constructed in the previous case. Now, let's talk about diodes in solar panels. In solar panels, it is necessary to add additional components such as diodes to bypass the shaded or damaged parts of the photovoltaic cell and to ensure that power is constantly produced. For this purpose, there are two types of diodes that are used, which are called the bypass diodes and the blocking diodes. Although these two diodes are physically similar in nature, the way they operate are different. The way they are integrated in the circuit are different. So the figure represents a circuit of a solar cell where we have the bypass diodes connected in parallel to the solar cell, and we have the blocking diodes implemented in the series combination of the photovoltaic cells. So let's understand the working of this circuit in a better light. So the bypass diodes are essentially the diodes that provide separate path for the current to flow when a certain solar panel is shaded or damaged. So let us just assume that this second solar panel is sort of damaged. In this case, essentially what happens is that the current flowing in this branch would be bypassed through this diode. As this diode is forward biased, it would act as a short circuited component. So the current would pass through this path and then would eventually end up at the output terminal. Whereas if the solar panel is not damaged, then the voltage produced by the solar panel would eventually pass through this circuit, and then the diode would become reverse biased. So the circuit would be an open circuited system, and thus the current produced through these two cells would be flowing in the natural way. Uh, Coming to the blocking diodes, let us assume that there is a DC voltage source that is connected across the output terminals here. And then when the solar cell setup is producing less voltage than the DC voltage source, naturally by convention, the DC voltage source produces some current in the backward direction. Thus, to prevent this, blocking diodes are being implemented so that whenever there is a back current that is passing through the diode, that is passing through the circuit, the diodes would be reverse biased and they would become open circuited, thus preventing any kind of reverse current that would be passing through this circuit. So to conclude, we have seen the usage of diodes as voltage multipliers. We have also analyzed the usage of diodes in the efficient working of solar panels. And finally, I would like to thank professors and course coordinators of ELL101 course for giving me this opportunity. And thank you.